Might as well get started. Hello, everybody.
Bonjour.
Hello.
How is everybody today?
Good. Shit.
Good. I kind of feel like today is a more chill day for whatever reason. Maybe.
Because it's raining.
Because it's raining, yeah.
There's no one here.
Bit chill in a sort of a mood sense and a temperature sense. Yeah. I'll just make the announcement officially because I just decided this. I'm not going to have time to put together an assignment 4 for you guys, unfortunately. If I were able to do it, it would be like I would be able to make maybe one question, calculate like a depth first search on some graph. That's like as much as I would have time to put together, and it's really like I don't want 7% of your final grade based on whether you answer one question correctly. That just doesn't seem fair. So the plan that we had before that I talked about is the plan that we will now enact. That 7% for the final assignment will go either against your already existing assignment grades, or I'll put it on the final exam. Whichever of the two of those is of more benefit to your final grade. Okay? I think that's fair. I'd like to apologize sincerely for not being able to make the obligations laid out in the course outline, but as I'm sure everybody here is aware, there have been a certain number of extenuating circumstances. So yeah. Good. Question?
Assignment 3, is that one like auto-graded? A lot of people are assuming it's auto-graded for anything. That one back soon, or?
Yes, I have one TA remaining, and I told her if she doesn't auto-grade it, then she's not getting paid.
Nice.
Because she's not unionized right now. So I can say, listen, if you don't do your work, you don't get the money, which is something you can't usually say to people. Yes?
Could you technically screw her over even if she does the work because she's not unionized?
I totally could, because she's not unionized right now, and the union isn't protecting her. She could totally do all the work for me. I could send an email to Lori saying she didn't do anything, and then she doesn't get paid.
Yeah.
But will you do that?
No, probably not, because I'm not evil. Like, well, you know. I try not to be evil. I try to repress my evil urges.
It's a joke.
I'll tell you, though, she's certainly not getting any bonus pay.
Oh.
Wait, do they get
Dr.
one?
Moore Joker.
So the thing that the department has been doing to try to, I'm not sure if this is official policy. I got in trouble recently for saying things that weren't official policy to people. I got called into the principal's office. But I'm not sure if this is official policy, if I'm allowed to say this, but I'll say it anyway, because, you know. Some of the TAs have been being paid double for picking up the work that's not being done by the TAs on strike.
Oh.
So, yeah. In a course where 4 out of 5 of the TAs have left, it is reasonable to assume that the remaining TA might be able to pick up, you know, double hours. But from my perspective, you only get double hours if you do double work. So, you know, there you go. And that's kind of, you know. There we go. So, yeah. Anyway. We should continue to talk about graph theory, yeah? So, recapping things briefly from last class, I know that like the fact that I do the recaps is like one of the reasons we're not going to get to string algorithms, but I feel it's still useful to do. I have no idea how this course was run last year, getting all the way to string algorithms. Like we've been keeping a pretty good pace, right? Like, I've been trying to present the material at a pace where people are actually understanding the material. So, you know, I hope that you'll forgive me for not... it's clear to me now we won't be able to get to string algorithms at all. So, I apologize for that. Yes?
Even if you're not getting to string algorithms, will you still be posting the slides for our
Yeah, sure. Yeah, absolutely. I'll post the slides so that you guys can take a look at that stuff because they're also very useful. But I kind of feel like that territory is going to be traveled in other classes that you're going to take anyways. Like, have they talked to you about finite state automata yet?
What?
I think that's next semester.
Next semester? Well, that's string algorithms and finite state automata are very similar kind of ideas. String algorithms, basically what we're talking about is the algorithms behind regular expressions and other similar sorts of topics. So they probably didn't even do regular expressions in 1xc3 when you guys took it, right?
A
Did they?
regex? Wait, regex?
Yeah.
We did a bit, but
A bit, yeah.
but I'll be honest, none of us remember that stuff.
Were you ever actually required to use the knowledge about regex?
Exam.
No?
The exam.
Like very.
Anyway, so I don't have time to get into it, but when you guys cover finite state automata coming up in more classes that you're going to take, then hopefully it'll retread the same ground. However, I don't think you will get as thorough a treatment of graph algorithms as you're getting right now in this course, in any other course, so this is the more important material to cover, in my view. If I were to do this course over again, I would probably cut the union find stuff. I think that wasted a bunch of time at the beginning. But anyway, so graphs then. So we've talked about undirected graphs, we've talked about directed graphs, and now we are talking about edge-weighted graphs. Edge-weighted graphs, of course, are undirected graphs where we apply a number to each of the edges in order to specify, characterize something about that edge. You'll find that edge-weighted graphs are extremely practical. Most of the time when you're dealing with graphs, there will be something interesting about the edges and not just simply the fact an edge exists. So, because we now have a bunch of numbers here, one of the things we are now interested in computing is we start introducing problems like how do you connect the nodes in a graph, in such a manner that you are minimizing the weights of the edges required. Maximizing is, of course, also a possible problem. As with many of these things, you just change the greater than to a less than, and a minimization algorithm becomes a maximization problem, right? So, in general, we are trying to compute what's called a minimum spanning tree. A minimum spanning tree is a tree a tree which includes every vertex in the graph, which also includes the minimal edge weight connections of all possible spanning trees, right? So remember that trees are acyclic, right? That's a property that's going to be very important when we start designing algorithms and reasoning about their correctness here. So, so we just started getting into thinking about cuts. The cutbacks are a-coming, folks. So, when we have a cut in a graph, we are taking the vertices of the graph, deciding that a certain number should be on one half of the cut, and a certain number and the rest should be on the other half of the cut, right? There's sort of this inclination, particularly in the slides, to imagine cuts as being straight lines through graphs. This is not actually true. You can have, like, in a very technical sense, a cut can be any division of the vertices, even in such a way that the vertices, once divided, are not connected to each other, right? So if we imagine, you know, reasonably simple graph, we might construe a cut like this, right? So in general, once we start, you know, making inductive arguments on like performing a series of cuts, we're going to start making assumptions that, you know, both of these, you know, at least, shall we say, at least one of these is going to be a connected cluster of nodes, right? However, in technical point of fact, this is a valid cut as well, despite the fact that we have, you know, in some sense cut this graph into 4 individual components, right? A cut is any division of vertices where neither set of vertices is empty. Make sense? Good. That's kind of a corner case. We're not going to see many of these. I just wanted to put it out there that this is theoretically possible, right? So when we talk about cuts later on, we'll be talking about more specific kinds of cuts than this, right? Make sense? Man, I wish they hadn't bought that terrible chalk. I'm going to be complaining about that for a while. So let's imagine that we have a more regular kind of graph and a more sensible type of cut, right? We now, it's a very simple definition. This should be fairly intuitive. We need to recognize the existence of what we call crossing edges, right? So if this is the cut line, any edge that connects vertices in one half and vertices in the other half is what we call a crossing edge. Make sense? That's going to be important nomenclature coming up because, you know, crossing edges are going to have certain properties. Question?
Is it only possible to have one cut in the graph?
Normally we'll only talk about one cut at a time. However, so here are some spoilers, all right? We're going to see in a couple of slides that if you take the crossing edges of any cut, the minimum of those crossing edges must be in the minimum spanning tree. So one algorithm, it's not the most efficient algorithm, but one algorithm for computing the minimum spanning tree is to do a series of cuts which include, like you start off with a cut containing one element on one side, add the elements to it one at a time. Each cut that you make tells you what crossing edge is in the minimum spanning tree. And by, you know, eventually cutting each vertex out and then, you know, calculating which edge must be in the minimum spanning tree, that's one way of calculating the minimum spanning tree. Make sense? Yeah. Don't worry though, we'll see that in slides. So, there we go. So, our cut property, given any cut, the crossing edge of the minimum weight is in the minimum spanning tree. Proof. The cut, so suppose that a minimum weighted crossing edge is not in the minimum spanning tree, right? So this will be proof by contradiction. And this is, you know, another one of these proofs in this class. It's not exactly a calc check proof. Have you guys been introduced to the awe and majesty of calc check yet? No? Wow. You'll see. Calc check is a utility that was written by Dr. Wolfram Call to be able to grade people on formal mathematical proofs, and you will be using it quite a lot if you take any classes with him, I'm sure. But so let's do a simple example on the board, right? So let's say we've got 1, 2, 3, 4, right? So, minimum spanning tree then. Can anybody figure it out just by looking at it? So in order to connect all 4 of these vertices, we need to use 3 of the edges, right? Which edge do we not take? Yeah.
The 4. We don't take the 4.
Right, because it's the maximum, right? So going into this, we know that our minimum spanning tree, I'm just going to do it as squiggles, is going to be that. Right? That's what we know to be in theory. So for the time being, let's assume that we don't know that, right? Let's assume that 4 is in the spanning tree, right? For the purposes of this proof. Cut it right down the middle, right? So we've got 2 edges, 2 and 4, right? Let's assume that 4 is in the spanning tree for now, or in the minimum spanning tree, right? So it's a tree, so we can't include, we can't create a cycle, right? So if our spanning tree is currently the dotted lines here, right? To include 2 would make that into a cycle, which would mean that it's not a tree anymore. So we can't include it there, right? Some other edge f in the cycle must be a crossing edge, right? So if you've got, you know, if it's a spanning, so there's kind of a hidden property here, right? If you have a graph, and you have a cut, if you have a cut of a graph, and there's only one edge, there's only one crossing edge, it must be in the spanning tree no matter what its value is. Right? Make sense? Right? Because how else are you going to get from here to there? Right? So, if you have an edge that was not selected, that implies the existence of another one that was. Right? With me so far? Good. So, removing F and adding E also creates a spanning tree. So if we were to construct a spanning tree of this graph, and I realize I've moved, this one's too confusing now. Too confusing! There. So, we can construct a spanning tree using either of these edges, right? We can't use both because that would always create a cycle, right? But we can swap one for another. Pardon me. So, since the weight of E, let's say this is E and this is F, if we take F out and replace it with E, we will count, and assuming the weight of E is less than the weight of F, performing that operation results in a spanning tree with a lower total weight, right? This contradicts the fact that we thought that F was a part of the minimum spanning tree. Therefore, it's not a part of the minimum spanning tree. E is a part of the minimum spanning tree, right? Question?
If a cut makes two crossing edges, but you include both of them, it does not make a cycle.
Yes, it will. If the rest, so, okay. So you have to think about these guys as already including spanning trees, right? So let's imagine that we have two spanning trees going on here already, right? If you include both, because each of these vertices is already in a spanning tree, each vertex is already connected up. So if you include both of these, you will necessarily create a cycle, and not just in this example, right? If you go back to our example of, 4 corners of a square, if you have a spanning tree, 2 spanning trees like this, including both of these would create a cycle. Make sense? Question? Follow-up question?
It's just, if you have something like this, would not both lines have, but it's not a spanning tree really. Because, so, like, both lines would be included.
Yes. So this is the question that's been asked. What about this one? Right? So here we are, again, hitting on that hidden property that they're not talking about in the slides, despite the fact that they should be. There's an implicit assumption, now that we're talking about minimum spanning trees, and that is that when you perform a cut, there is a spanning tree possible on either side, right? So with respect to this algorithm now, right, they've added this hidden property that, when you make a cut, all of the vertices on either side of the cut can be connected to each other, right? They've now made this decision. They never told anybody that they made this decision, but they made this decision. So, essentially, you're absolutely correct. In this situation, the correct spanning tree crosses that line twice. Absolutely, it can't not. However, this would be considered an invalid tree according to the hidden property they're not telling us about. Does that make sense? Yeah. And perhaps it's just because they defined cuts poorly here, right? Basically, all of that business that I've been talking about, technically a cut can mean this, but they don't mean that. This is my sort of roundabout way of criticizing the slides and saying to you as a class that in the slides, the cut operation has been defined poorly. It hasn't been defined specifically enough to exclude cases like that, which is why I'm talking about it having hidden properties that are not mentioned in the slides. Which is why you need a professor, and you can't just learn everything from the textbook, because this is they probably omit that in the textbook as well, unless the person making these slides didn't read the textbook, but So far the slides have been based pretty heavily on the textbook, so like all the diagrams are out of the textbook, so anyway. So have I satisfied everybody in the room that when you perform a cut, the minimum crossing edge is in the minimum spanning tree? Everybody satisfied? Excellent. Collaborative mathematics. So, new property, cycle property. Let C be any cycle, and let F be the maximum cost, the edge of maximum cost within that cycle. The MST must not contain F. Make sense? So basically, another way that you can, like, if you were concerned about calculating it this way, which, you know, we're going to look at more efficient algorithms for calculating this, but one thing you could do is you could go through your graph, analyzing every cycle, right? Sort of marking the edges as included or excluded, right? Go through every cycle, mark the maximum edge in that cycle as excluded, and then at the end of that you might have a minimum spanning tree. You might also still have some redundant edges. But in theory, once you do that, the graph should be entirely acyclic because you've broken every cycle, right? So that might also be a way to calculate the minimum spanning tree now that I'm thinking about it. But yes, so proof. All right. Let C be any cycle, right? Let F be the max cost edge belonging to C, and let us, So, I don't know why they're introducing T star without actually explaining what T star is. T star will be the minimum spanning tree. T stands for tree. So, let's suppose that F belongs to the minimum spanning tree. Again, this will be proof by contradiction. So, deleting F from the minimum spanning tree disconnects the minimum spanning tree, right? One of the things about a spanning tree, because it doesn't contain any cycles, it also doesn't contain any redundant connections. If you remove but a single connection from a spanning tree, it is no longer a spanning tree. Right? Good. So, deleting F from T star disconnects T star, or the minimum spanning tree. Let S be one side of the cut. S being a set, right? So we have the set of nodes S, all right? Some other edge in C, let's call it E, has exactly one endpoint in S, right? So T, that's T here, is equal to T star union E minus F. That's, T is our new spanning tree. That's also a spanning tree. So this is a little bit confusing, but I'll give you a simple example. Too short. There we go. Although it was good chop. All right. So here's our graph. We're assuming that our minimum spanning tree includes F, right? But it does not include E for some cut, right? So if this tree is T star, then a new tree, just T, which includes E but not F, we are going to call that T. So, with dotted lines. So, make sense? So we're talking about two different trees here. T includes E, T star includes F. Otherwise, they contain all the same connections. Make sense? So really, what's represented by T star and T is a decision about whether E or F is being included. Make sense? So far? So far, so good? Since the cost incidentally is also weight, Like, I kind of get the impression that these slides were like composited from multiple people because we've suddenly switched all of our naming conventions for no particular reason. Cost means weight. So it's the weight of the edges, also the cost of the edges. Since the cost of E is less than the cost of F, the cost of T is less than the cost of T star, right? Makes sense. This contradicts the minimality of T star, right? So, basically, so let's imagine that, we have numbers here. One, two, three, four, five, right? The total cost of T star will be 1 plus 2 plus 5 plus 4, which is 12, thank you. And the cost of T, I think it's a fair question. The cost of T, 1 plus 2 plus 3 plus 4, what's that? Huh? 10. It's also kind of fun because, the first 4 natural numbers aside, the first 5, if you include 0, sum to 10, which is kind of fun. It's like one of those little interesting numerical properties. But anyway, cost of T is less than cost of T star. We went into this assuming that F was in the minimum spanning tree and that was that T star was the minimum spanning tree. Turns out it's not the minimum spanning tree, but just a spanning tree, right? Therefore, by swapping F for E, we have further minimized the minimum spanning tree, right? But the only reason this works is because if you were to connect up all of them, you would get a cycle, right? With me so far? Cool. So, here we go. So let's talk about Causcos algorithm. Causcos algorithm for calculating the minimum spanning tree. So, in Causcos algorithm, we consider edges in ascending order of weight. That's very critical, right? So we have to sort the edges by weight before consideration, right? It kind of stands to reason that the minimum spanning tree should include all of the smallest numbers in the edge weights, right? Although that's not necessarily going to always be the case, but, well, no, it is. It is all the case. I thought I had a contradictory case in my head, but it turns out that was a bad case. So, yes, Causcos algorithm does work. There's a reason it's in the slides. So, add next edge to tree, unless doing so would create a cycle. So, in order to perform Causcos algorithm, we need to be constantly, at each step, checking the thing to see if introducing this new edge has created a cycle, and if it has created a cycle, we sort of walk that back, drop that edge, and consider the next one, right? So y'all remember what algorithm we use to determine whether a tree has a cycle? What is it?
I don't know the name.
Hmm?
I can't remember the name of it.
Starts with a D. Depth first search. Remember the example of depth first search we did where we kept the on stack array that checked to see if the edge that we are going to is on the stack or not? That's a cycle detection algorithm, right? So we use cycle detection depth first search to detect whether or not introducing a new edge introduces a cycle, right? So in this particular, you know what? Yeah, I think it's better doing it on the board, so I'm just going to do it on the board. Ta-da! So, Causcos algorithm. First, we consider the edges in order of weight, starting with the smallest. So, 1, add that to the tree. 2, add that to the tree. That does not create a cycle. 3, add this to the tree. Does not create a cycle. 4, add this to the tree. Does not create a cycle. 5, add this to the tree. Does not create a cycle. Wow, this is a terrible example because I'm going to... There. Now it's a less terrible example. 5.5. We examine this. Adding it would create a cycle, yes or no? Yes. So we exclude it. 6, adding this would not create a cycle, so we include it. 7, cycle. 8, cycle, so we exclude them. So that is the minimum spanning tree of that graph. Make sense? Relatively straightforward. Complexity. Given that we require depth first search to perform the cycle checking. Yes?
Is it edges plus the cardinality of edges plus cardinality of vertices?
Say that again, please.
Cardinality of vertices plus cardinality of edges.
Well, that's certainly part of it. So depth first search is cardinality of vertices plus cardinality of edges. Right? What is this iterating over? Edges. Is it iterating over vertices at all? No. So, we perform this a number of times equal to the number of edges. Right? Now, of course, we're going to have a similar thing going on with, like, oh my god, I hate the fact this can't be erased fully. So this guy, right, is going to be operating on subgraphs, right? It's a very, like, the analogous situation is where you're doing something over, like bubble sort, right? Where the portion of the thing that you're sorting decreases in size over time, right? This is the inverse. The size of the thing you're performing depth first search on over time is increasing, right? To eventually encompass all of the vertexes and all of the edges in the final step. But, you know, that, right? So here's a question. Here's a question as well, right? Basically, that means we've got big O of EV plus E squared, right? Because there's a step I'm leaving out here, right? We have to also sort the edges by weight, right? So how long does it take to sort something? If you're using, like, let's say, a half-decent sorting algorithm? Right at the back, sir. N log N. Yes. Or in this case, E log E, right? However, what's larger, E squared or E log E? E squared. So we don't even have to worry about it. Right? Make sense? Good. So that's Kruskal's algorithm. Yes?
I have a question about the example on the slide.
Yep.
So if you connect 0 and 5, which would be 0.6, wouldn't that be shorter than connecting 3 and 4 and 7 and 4?
Okay. 3, 4, and 7, 4. Yeah, but you still have to connect 4 has to be included somehow anyway, right? Yeah. So that's a good question, though. So in this particular example, right, the question is, isn't it more efficient to include 0, 5, which has an edge weight of 0.6, rather than including both 3, 4, and 4, 7 in order to connect 5 to the rest of the tree, right? And from that perspective, actually, yes, if you consider the edge weights of 3, 4, and 4, 7, 3, 4 being, 4, 7 is 0.46, and 3, 4 is 0.34. Wow. So obviously the sum of those two is greater than 0.6. But we're going to need one of the two of those anyways, right? Because if we were to leave both of those out, 4 would remain unconnected, right? And in order for it to be a minimum spanning tree, it needs to be a spanning tree, which means every vertex needs to be included. So at maximum, we get to throw out one edge and make a different decision about it, right? Since, and this is kind of like, this is like a roundabout way of reintroducing the cut property that we were talking about, right? Because you can only make one substitution of an edge for another edge, right? And without breaking the spanning tree, certainly, neither 4, 7 nor 3, 4 is greater in weight than 0, 5. So they are, in fact, the correct decision, despite the fact there are two of them, right? Because you gotta connect 4 as well. Does that make sense? Any other questions? Yes?
Do we also need to have something to check to make sure all the vertices are connected so we don't keep continuing? At the end, we checked 7 and we checked 8 just to make sure it didn't perform a cycle, but they were all connected anyways. So then we keep continuing.
Do we have we talked about an algorithm that checks to see if something's checks to see if something's a spanning tree? I mean, so in theory what you could do is you could keep a marked array, right? And anything that gets included in the spanning tree gets marked off in the marked array, so you could cut the algorithm short once every vertex is in the marked array. That would be one way of performing that operation and, truncating it before you perform all of these additional operations. That would be a good improvement because, there are likely to be quite a few of these, right? And they're the most expensive ones to calculate the cycles for, right? So good optimization. There was another question around here, was it?
So I was basically trying to answer the same question because I noticed that after you connect edge 6, you have all vertices connected.
Yeah, we're done. Yeah. I would say a marked array is a good way to go about that. That's certainly how we've done things in the past. Spend a little memory, get a lot of runtime. Any other questions? Right at the back.
So before
Yes. Yeah,
Would that be like a linked list or like an array or something, or you would be supplying that into Causcos Algorithm?
It depends on how you want to do it. I would think that,
You can't just give it the graph, because it wouldn't know how to use it.
correct, yeah. So Causcos algorithm requires as a precondition that that you have a list or an array of the edges sorted by weight, right? That's your precondition to Causcos algorithm working. However, unless your data structure is already maintaining a sorted list of your edges, right? Which kind of, like, in order to do that, you would need to, like, predict that you're going to be running Causcos algorithm a lot, right? I could see a scenario where, like, you wouldn't maintain that data, right? But yeah, in theory, you could construct the data structure in such a manner that in addition to the adjacency matrix, you're also keeping a sorted list of the edges so as to speed up Causcos algorithm. Because, of course, you know, if you're doing it with an array, maintaining a sorted array is a logarithmic algorithm every time you add an edge, right? So it's, you know, and we're still, hello? So we're still sort of, if we take a look at our API, right? We are, we've now added the ability to add a bunch of edges all at once. Adding, you know, a logarithmic component to that doesn't necessarily make it more complex in a way that's harmful, you know, especially if it speeds things up later on. But, you know, it's kind of like, we're still in a situation where the pre-processing does not outweigh the runtime of the algorithm itself, so it's reasonable to do the pre-processing, you know, when the algorithm itself is run, but it's more efficient to have it done up front if it's being done a lot, you know. We're kind of in one of those gray areas where whether you want to do the pre-processing up front every time or whether you want to keep a data structure which keeps that information already in place. It's kind of like, that's an intelligent decision that should be made by an intelligent designer based on the situation they're in. Cool. Any other questions? Lots of good questions today. All right. Thank you very much, folks. We will see you guys on Friday.